Thank you very much. Yeah, thanks, Konstantin, for the kind introduction. I'd like to also thank all the FHI-aims team for, first of all, writing the code, but also organizing this webinar. And finally, I'd like to thank the audience for listening to my talk. So today I would like to talk a bit about solid electrolytes and how we can model them using FHI-aims. As you all know, solid electrolytes are components of solid-state batteries. And of course, solid-state batteries are becoming of increasing importance in our technological world. And in particular, solid electrolytes are components that actually provide the source of lithium ions in solid-state batteries. Now, those materials are quite complex, so they're usually composed of a cationic framework, which is rather immobile, and anionic framework, which is immobile, and cationic lithium, part of the framework, which is actually mobile, right? Which is exactly the source of the lithium ions. And so there's a lot of puzzles, what I call ionic puzzles, in those materials that we need to solve in order to understand their properties and their functionality in real world. I'd like to start my talk in a very broad way by first telling you a bit about what I see is the main challenges in the field of atomistic modeling. So I'd like to start with this picture of what I call now the standard model of atomistic modeling, which relies on three fundamental pillars. Quantum mechanics, which is the main topic today. It gives us the ability with certain approximations to compute hopefully accurate forces that atoms feel in molecules and solids. Now, of course, that's not enough in order to understand the behavior of materials. We usually need to understand how things evolve under given conditions of temperature, pressure, and external environments. For that, we use statistical mechanics. And finally, machine learning is a fundamental third pillar that enables us not only to accelerate both quantum and statistical mechanics calculations, but also actually form statistical representations of how properties evolve in molecular and material spaces. But of course, all these pillars, really, I think the most fundamental pillar is that of quantum mechanics. Because if we make errors in our quantum mechanical force calculations, those errors will propagate often in an uncontrollable way into our statistical properties or into our machine learning potentials. So as we go about constructing more and more general or universal machine learning potential, it becomes especially very relevant to really have a very precise and accurate description of quantum mechanical forces. Now, usually we employ density functional theory to compute our approximation for quantum mechanical forces. And of course, DFT is in principle exact, but in practice, there is a price to pay, and we use density functional approximations, or DFAs. So what DFT does is it achieves, in principle, a mapping from a many-body wave function, which is a 3n-dimensional object, where n is the number of our quantum particles, to an effective three-dimensional electron density representation. Now, of course, there is a price to pay for this, in principle, very efficient mapping of what I would call a no-free lunch, because we end up having to approximate all the many-body exchange and correlation effects. And usually we do this by so-called semi-local or hybrid functionals, which are based on local and then increasingly non-local information in the electron density. So we start with the LDA approximation, we go to use the gradient and the GGA approximation, then we can use higher order derivatives of the density or the computing the exact exchange energy in hybrid functions. So this, of course, leads to well-known self-interaction errors that we usually alleviate by using hybrid functionals such as PBE0 or HSE. And then, of course, the second part which is missing is, so actually when we improve the exchange energy, we usually improve the electrostatics of our system. We also improve the description of Pauli repulsion. But of course, as you all know, semi-local functionals also miss the description of long-range correlations, and that, of course, subsumes the very important van der Waals interactions that Mariana already talked about quite a bit. So, of course, we also know in principle how to treat the long-range electron correlation in the context of density functional theory that requires us to go to so-called adiabatic connection fluctuation dissipation theorem approaches, which provide a non-local approximation to exchange and correlation energy. And here we kind of get some free lunch because we actually know what quantity we need to model. And this is so-called the density-density response function chi, which is a non-local function that measures the change of potential at point r prime, the change of the density at point r prime, to a change of the potential at point r. So, well, this function is, of course, a non-local and highly complicated function, time or frequency dependent as well. Nevertheless, if we could construct good approximations to this function, you could, in principle, get a very reliable way to include non-local electron correlations, van der Waals interactions, and so on. Now, usually we use so-called random phase approximation to construct this function, but that's also quite expensive for realistic materials. And so we end up doing something like this on the bottom of the slide. So instead of actually modeling the response function, we only model the van der Waals or the London dispersion part of it, right? And this can be done by multiple ways. For example, fragment-based approaches. This subsumes the Grimes DFTD approaches, D2, D3, D4, the exchange dipole moment XDM approach of Beck and Johnson, or the Tkatchenko-Scheffler approach. The two-point density functionals, such as the VDWDF functional of Langres and Lundquist, or the Vidrov-van Voorhis functional, are also doing something very similar. Essentially, although the formulas of these approaches look a bit different, but the physics underlying them is actually very similar. What you do is you define the polarizability of some local objects, and you compute the pairwise energy, the pairwise interaction between those objects. So some time ago, as Mariana also said, we've developed the MBD approach that essentially uses exactly the same formula as the exact adiabatic connection fluctuation dissipation theorem approach, but instead it's providing a model for the density-density response function using localized harmonic oscillators. Once you've parameterized those harmonic oscillators from the density using actually the Tkatchenko-Scheffler approximation, you can couple them and solve the ACFDT equation to infinite order in perturbation theory. Once you do that, you get two-body effects, three-body effects, n-body and infinite order effects, actually, and that's the approach which we often use. Then in 2020, we went beyond this and we tried to actually make a broadly applicable functional for DFA plus van der Waals functional that actually can describe molecules, materials, and all classes of different materials on equal footing. We did this together with Jan Herman, who was a PhD and a postdoc in my group. And so essentially, the essential idea here is to get what I would call the best of both worlds. So we combine a two-point non-local functional of Vidrov-van Voorhis. We renormalize it to make it exact for the whole periodic table. And then we use this renormalized VV10 polarizabilities and employ this as an input to the MBD Hamiltonian. And then we solve the MBD Hamiltonian to get the many-body energy of, or the many-body long-range correlation energy of your system. So this really joins together two very general concepts in the field of van der Waals interactions, the non-local functionals and the MBD approach. And we've demonstrated that this actually works quite well for a wide range of molecules, materials, metals, ionic solids, and so on and so forth. And that's, of course, as Mariana said, implemented in the FHI-aims code. Just to show how this works, so here on the left, I show you a performance of the MBDNL functional together with the PBE DFA for molecules, the S66 dataset on the left, and for 64 solids on the right, including metals, simple metals, transition metals, semiconductors, carbides, nitrides, and ionic crystals. And you can see that for molecules, it performs as well as the traditional molecular MBD at RSSES functional. This is very good performance. It's better than the VV functional. You see that in the VV functional, you get inconsistent accuracy as a function of separation distance between molecules. And also for solids, the performance is not far from the performance of the parent PBE functional. Now, it's pretty hard to beat PBE. Actually, no one really beats PBE still, I would say, in terms of local, semi-local DFT functionals in terms of performance for solid state. In contrast, so PBE plus MBDNL works as well as PBE. In contrast, the original MBD functional fails for many of the solids because of so-called overpolarization problems. And so you cannot even carry out MBD calculations for many of the highly polarizable solids. Okay, so now let me go back a bit into the history as well to review what we understand actually about van der Waals interactions in hard solids. So it's not a surprise that van der Waals interactions or dispersion interactions are extremely important for molecular solids. For example, the benzene molecular crystal would not even assemble if you don't have the correct description of van der Waals interactions. But for hard solids, it turns out that we actually know very little about van der Waals interactions, even up to date. So here is our early work. I think this is really the first work together with my former student, Guoshu Zhang, who I hope is also hearing today. We asked the question of, can we really understand how important or not important van der Waals interactions are in ionic and semiconductor solids? And in this paper, we actually demonstrated that if you take PBE or HSC functionals and you add van der Waals dispersion interactions to it, all the properties, all the cohesive properties, lattice constant, cohesive energy, and bulk modulus actually improves. We only did this for 6 ionic and semiconductor solids, and then in 2018, we went ahead and actually did it for a large range of solids. In this case, this is the example of 23 semiconductor solids, where you can see that the inclusion of van der Waals interactions in HSC functional in particular actually gives you results that improve on the parent functional always for the lattice constant, the cohesive energy, and the bulk modulus at the same time. And actually, this gives you always results which are much better than the PBE sol functional, for example, which is still widely used to describe solid properties. And it's actually on the same level of accuracy as the scan functional, which is, of course, much more sophisticated and more expensive, and actually still needs to be corrected for van der Waals interactions. Of course, we are not the only people that worked on the importance of van der Waals interactions in solids. This is quite a prominent paper from Jire Klimesh and Angelos Michaelides, who demonstrated that by empirically optimizing semi-local exchange in density functional approximations and coupling this to non-local van der Waals functional of Langres and Lundqvist, can actually get better results than PBE for the cohesive energies of solids and get the lattice constant is essentially lattice constants of solids with actually the same accuracy as PBE. So this was quite a breakthrough. And of course, this is a widely used functionals, for example, the OB88 van der Waals function. Now going beyond solids, hard solids, to actually realistic solids, so solids with defects, which of course connects to the main topic of this talk, which is solid electrolytes. We also did early work with my former postdoc Van Gau at the Fritz Haber Institute, looking at what happens in terms of van der Waals interactions for defects in solids. So this is actually a work for silicon, right? This is simple silicon bulk, and silicon has 4 natural defects that are experimentally known. It has 3 different geometries for interstitials, so-called H, X, and T interstitials, and a vacancy. And in this work, we looked at how van der Waals interactions actually contributes to the properties, the stability, and the mobility of point defects in simple semiconductors. And we were extremely surprised because, semiconductors are, of course, tightly bound. They're chemically bound, and you usually do not consider van der Waals interactions to be very important. But we found in this work that for a particular migration between the H defect and X defect, the barrier actually is modified by 0.4 electron volts. It goes from 0.69 to 0.29 electron volts by including van der Waals interactions. And this modification of the barrier actually comes from two coupled effects. One is the modification of the geometry of your system in the presence of the defect. And the second one is that the transition state is actually the geometry of the transition state is also modified quite a bit. And so this is actually quite a surprise, and our results agree much better with the experiment, and were later actually confirmed in explicit random phase approximation calculations by the Cresses group. Now, of course, these calculations are extremely expensive. They had to use very large unit cells actually here, but they basically confirmed our HSE plus van der Waals results with the RPA calculations. So this is just to tell you that the inclusion of van der Waals interactions stabilizes or sometimes destabilizes your system depending on the property that you are studying. So this was the, let's say, old history. And now let me go to the main topic of my talk, which is the description of solid electrolytes. And in particular, once again, we will focus on the stability and the mobility of these complex materials. So this is work which we've done together with Swastika Banerjee, who was a postdoc in my group, and she's now assistant professor at IIT Roorkee in India. And the results of this work actually are about to be published in Nature Communications. So this paper is in press. So in particular, first of all calculations that I've been presenting, I will be presenting are done within FHI-aims using a variety of functionals, and I will comment on this later. So what we are interested in particular, we focus on the so-called argyrodite family of lithium supraionic conductors. These are so-called quaternary materials. So they have four components. You have, of course, lithium cations. You have halogens, you have sulfur anions, and then you have a semi-metal. It can be phosphorus, silicon, or germanium. And so, as you can imagine, this combination of four components, four elements, can give rise to a large chemical space and a large wide set of properties of these materials in terms of both the stability and the mobility of lithium ions through these materials. These materials often alternate between ordered structures and disordered structures, so there can be disorder between the halogens and the sulfur atoms, and this again just makes the chemical space even more complicated. And so we would like to understand this chemical space, and in particular, we would like to understand what level of theory is required to actually accurately model the stability and mobility of these materials. So as I said, the materials are characterized by having essentially an almost immobile anionic framework, right? And then the lithium is diffusing through the material. So that's the mobile part. And so you need to kind of be on this verge of stability and instability in order to enable high enough mobility of lithium ions. And so we will focus in particular on four different types of argyrodites. So you have chlorine-based, iodine-based, mixed anion, and mixed cation. These materials have been experimentally characterized, and the ion mobility has been actually measured. So as you can see here on the sigma RT, this is the room temperature ion mobility, ion conductivity, let's say. You can see that it can vary by 4 orders of magnitude, depending on the particular structure of the material. So it varies, between 10 to the minus 3 to 24. And in particular, it's not known why. So for example, if you look at the chlorine-based or iodine-based material, the iodine-based one has a very low mobility. But people were actually expecting that the inverse would happen because iodine is a highly polarizable ion compared to chlorine. And so people were expecting that higher polarizability should actually correlate to higher mobility. But instead, something different happens, right? Something contrary happens. And so this remains unexplained. If you look at the right-hand side, this is the average barriers that have been experimentally measured for ion mobility. And you see that actually they are all, they don't change too much depending on the material, which means that the pre-factor, which essentially measures how many different pathways for diffusion exist in this material, right, are there. So you need to understand both the pre-factor, all the different pathways for lithium mobility, and also the barriers. So let's first look, in order to understand the mobility, we first need to understand the stability, the general stability of the material. Let us start by looking just at the global structure of these materials by measuring the cell volume. So we look now at just two of these materials, the chlorine-based and the iodine-based argyrodates. So the experimental volumes are in blue and green here on the left. And so you can see that semi-local functionals, PBE or HSE, actually give pretty bad results. If you include van der Waals interactions, for example, using the Tkatchenko-Scheffler approach, you overstabilize those frameworks, although the difference in volume between the two materials seems to be actually accurately captured. PBE plus 3-MeS-D3 seems to work well, but actually, if you move to HSE plus D3, which is just a change of the functional, the results are much worse. And this is actually surprising. We don't understand why there's such sensitivity to change in the parent functional that actually does not happen with the Tkatchenko-Scheffler approach, which gives exactly the same results from PBE to HSE. On the other hand, the PBE Sol functional, the OP-B88 functional, actually are not giving too bad results, although sometimes they underpredict the difference in volume between the two different structures. Now let's look at the right, at the HSE plus MBDNL functional, which to me is really the only approach that includes the non-locality in both the exchange and in the correlation energy. And if you do that, you see that the results are getting actually pretty close to experiment, in particular if you go from 0K structure to 300K structure by including vibrational unharmonicity and 0-point energy correction. And you see we get results which are pretty close to experiment. Now, of course, getting the global structure right is not the only thing you need, but you also need to focus on the local structure within the unit cell. So the argyrodite materials have very specific constraints because of their structure. For example, they usually have very symmetric chlorine-lithium bonds, and also this tetrahedra of the semi-metal with the sulfur. And so what we've done is that we've taken all possible argyrodite structures from the CSD data set, right, of crystal structures, and we've done just an average of those structures. And we've constructed, for example, here the GOVAR distribution of chlorine-lithium distances. And this is shown in black in this plot. One thing you immediately see is that at 3.5 angstrom, some functionals such as PBE Sol and OPT-PBE, OPT-B88, sorry, they lead to a peak which is absent from experiments. And this peak arises from an inhomogeneous distortion of lithium ions around a chlorine ion. And that's actually wrong, right? That shouldn't exist. That's not there in experiment. On the other hand, this symmetry is not present when you go to the highest level of theory, HSD plus MBDNL, and you get the correct homogeneous description of the bonding between chlorine and lithium. Okay. Overall, HSD plus MBDNL has a really, really good description here compared to experiment. We cannot compare one-to-one because we are doing a simple average over structures. But as you can see here, in particular, if you take the disordered structures in our calculations, we describe all the prominent peaks really well. Okay, so now we've assessed the stability and we've demonstrated that HSE plus MBDNL gives you both accurate global geometries and also local geometries in the unit cell. Now let's move to the lithium diffusion. So Swastika in her previous work have actually done ab initio molecular dynamics calculations for two different argyrodite materials, and she looked at how diffusion pathways vary from one material to the other. And what she has found in particular is that in this chlorine argyrodite, you have cage-like lithium diffusion. You see here these concentrated cages, while in mixed anionic material, which has the largest lithium conduction, you actually form this interconnected domains that form diffusion channels, and that explains why the lithium conductivity is so high in this mixed anionic materials. So there is a wide range of possible lithium jumps between the different parts of the framework. So in order to study this, we first focus on the shortest diffusion path for lithium diffusion in these two different materials. Again, the chlorine-containing material on the left and the iodine-containing material on the right. And let's look at the barriers here. So here is the, on the x-axis, you have the diffusion path. On the y-axis, you have the relative energy. And what you see is that depending on the functional, the pathway, the barrier is actually quite different. So in particular, if you include van der Waals interactions using the Tkatchenko-Scheffler approach, which is the pairwise approach, you see that the barrier is getting, the transition state is actually getting overstabilized. So the van der Waals energy is much higher in the transition state. This is this red dashed curve here, or the pink dashed curve. And for that reason, the barrier is actually very low. With the many-body MBDNL approach, the van der Waals energy is essentially homogeneous over the whole transition path. So it doesn't change. So there's a complete flat van der Waals energy, and that's why the barrier is actually much higher and also agrees much better with what the experiment actually sees. Although we cannot compare one-to-one, but that's what we would expect. We'd expect a higher barrier here, a bit lower barrier for chlorine, and that's actually consistent. One way to assess why this change in the barriers happens between pairwise description of van der Waals interactions and a many-body description is looking at the geometry of the framework in the minimum and in the transition state, right? So here the two columns are the minimum distances between lithium and sulfur atoms and lithium and halogen atoms. And on the right, the right two columns are actually the distances for the transition state. And as you can see in this pairwise dispersion, in the minimum configuration, in the equilibrium configuration, the difference in geometry between pairwise dispersion and many-body dispersion actually is very, very small. But when you move to the transition state geometries, you realize that there can be very drastic changes, especially for the mixed anion framework here. For example, the lithium chlorine distance actually changes from 3.47 to 2.81. It's a huge change in the geometry, which kind of agrees with our old work on diffusion of silicon, on defects in silicon, where we also observed quite significant differences in the geometry upon including van der Waals interactions. We see the same here. So basically, softer frameworks, which is exactly happens here for this mixed anionic framework, they can lead to very high changes in the distance due to the inclusion of many-body dispersion effects. That's quite surprising, but that actually explains why there's such large differences in the transition patterns.
3 minutes, please. Oh, yeah, almost done.
Yep, this brings me to my conclusion. So I have described a range of comprehensive calculations that we have done to understand different properties of solid electrolytes, in particular the argyrodite family. We found that the impact of non-local interactions, both in the exchange by using HSE functional and in the long-range correlation by using the MBDNL approach, actually has high impact on both the stability of these frameworks and the mobility of lithium ions through the framework. We saw that the really important thing to get right is the local structure of these materials, not just the global unit cell, which is what most people focus on, and in particular, the local structure of the structuring of sulfur and lithium ions actually can change quite a lot in the pairwise treatment of dispersion interactions versus MBDNL treatment of dispersion interactions. Once again, this work will be published soon in Nature Communications. And with that, I'd like to thank you for your attention.
Konstantin, and thanks, Alexander, for the nice talk. And I don't see any questions in the Q&A right now, so I'll just give a moment for people to type any, or again, if you want to speak your question, then just raise your hand. But maybe I could just start with a quick question. So in the chlorine lithium distances G of R plot you showed, why was the two peaks at the low distances at the experiments and just one peak for the theory?
Right. Yeah. So here one thing you can already see is that the level of disorder, right, it matters a lot, because, for example, if we move from the from this blue solid line to the blue dashed line, which is HSE plus NBDNL for an ordered structure and for a range of disordered structures, you already see quite some difference there, right? And the peak actually moves much closer to the experiment. There's some incipient change in the gradient of the dashed line if you look very closely here, although there's several overlapping lines, but we don't really get a peak, right? We just took I actually don't remember how many disorder structures we calculated, but we didn't really took all the disorder structures from the experiment, right? So it might be that we just subsample the structures where this particular second peak appears here.
Mm-hmm. Okay. Still nothing in the one has appeared in the Q&A. So let me just. So this is from Ramsevat Kashyap. So is dispersion also affecting paddle wheel effects, or are there vibrations? In my opinion, this can also affect the lithium migration.
Yeah, that's right. So in the paper, we actually look very carefully as well at the phonons of these different frameworks, and we do find that the dispersion, the treatment of dispersion interactions, has a very strong effect in the low frequency phonons that actually dictate the lithium migration through the framework. So yes, so actually the phonon modes change qualitatively depending on which treatment of dispersion interactions you have, and we have some arguments in the paper why actually the NBDNL phonons agree better with what is experimentally observed in the systems. But this is something where actually I think the next step would be to try to train machine learning potentials on this data and actually simulate dynamics and observe the actual lithium migration. And this would be the next thing to do in this system.
Thank you. So a question from Sandeep Kumar. So what are the best strategies for minimizing disorder in LMSX to achieve an optimized structure?
So the disorder is actually a natural phenomenon that happens in these materials, and in fact, because the highest mobility is observed in these mixed anion materials, right? Disorder is something that actually helps, right? The disorder is specifically between the halogens and sulfur. Actually, what helps to maximize the mobility. But of course, you want to have certain mobility, but you also want to have a certain stability, right? So you always optimizing for mobility and stability at the same time. And in fact, these mixed anions are also, I think they decompose electrochemically. So unfortunately, in order to optimize both properties, we don't have the answers yet how to do this. I think this will be the next thing to do, again, by explicit molecular dynamics simulations.
Thank you. And the question from Sandy, can ab initio molecular dynamics be done at the HSE 06 level in FHI-aims in a practical computational time for solid electrolytes or cathodes with transition metals?
So is the question whether we can carry out explicit ab initio MD?
Yeah, I guess carry out explicit ab initio MD with HSC 06 and in a reasonable time or with reasonable.
Okay, yeah. So what I would do is I would actually I would just construct a machine learning force field using the HSC plus NBDNL as forces as an input, right? I think that's what I would recommend, right? I think that the speed, as Mariana has discussed in her talk, the speed of HSC plus NBDNL calculations actually is sufficient to generate enough reference data to construct machine learning force fields here for these materials. I think you probably need just a few thousand calculations for a few thousand structures, which would allow you to construct, general machine learning force fields for this class of materials. We haven't done it, so it might be more complex than that. But I wouldn't actually recommend running explicit ab initio MD on the systems because I think that with machine learning force fields, that's the way to go now.
Can I just add, you can check the timings in that publication that we gave. You can see for your system size, more or less, what would be the cost. And if you have a really large computer, maybe the computational time won't be won't take many years, but the computational cost will be insane, okay? So doing explicit ab initio MD on these large disordered materials, I think, is not really the way to go in general. I agree with Alex completely. So yes, so a machine learning potential, but then the nice thing is that you can do large structures that capture all of this disorder in the training set because you can calculate quite a few points and that's it. But MD, you need hundreds and hundreds of thousands or even millions of evaluations, right? So it's another game.